Hello everybody, here is lesson 7 of our energy series, and nice little cap, I think, on the whole series here when now that we're going to look at power. We're going to look at power, but also how we can use efficiencies as well. All right, so let's have a little brief qualitative discussion on power. Quite simply, power is the energy, or I guess the change in the energy over time. Okay, so in this little scenario here, we have a girl who is going to run up some steps. Now, we could do a deep dive and talk about the gravitational potential, energies, etc., but just got on here the weight of the girl, and that's going to be mg. There's the normal force pushing up, which is the opposite of the weight. She starts with a zero velocity, and then obviously by the end she has a final velocity. So and we could also say that this is zero height. So we would go through our energy calculations saying that she has zero mechanical energy at the beginning, and then at the top of the steps she would have some value for mechanical energy that would consist of this kinetic energy here, plus the gravitational potential energy here. Now, if you took a measurement of the time, if you divided that by time, that would give you power. And it's as simple as that. So let's have a look at some more detail. Here's just a restatement of what we just said. Power is a change in the energy over time. Well, a change in the energy is also work. So work divided by time will give you the same value. And obviously we're going to be using our fundamental units, so joules and seconds, and that's the equivalent of a watt. So a watt is a derived unit, and if you want to keep going, it's a derived unit of a derived unit of a derived unit, because a joule is a Newton times meter. So Newton times meter divided by seconds is a watt. And of course, a Newton is a kilogram meters per second squared. And then if you times that by the meter, you get the squared. And then if you divide by seconds, you actually get to a third. So kilogram meters squared over seconds cubed is a watt. So it's a derived unit of a derived unit, if you like. Anyway, units are interesting. So, if you apply a force in the same direction, then you can also talk about this Newton meter. So there's the Newton, there's the meter. So Newton meter over time. But take a look at this. This is kind of neat. The Newton meter ends up giving you essentially a d over t. And you know that distance over time is velocity. So we can do some deriving of the units and look at the different parts of the equations and rearrange them and say them in a different way. So we actually get this statement that power is also force times the velocity, which is kind of interesting. Okay, let's look at an example, and then you will be good to go for your prep questions here. So one more thing to talk about then is just efficiency. We've talked about this in class quite a lot. I use the analogy often with test taking and getting a score on a test and then reporting the percentage that you score on the test. So efficiency is about how much energy is lost or is useful in a particular scenario. So we're really just comparing the outcome to the total beginnings amount. So this is why using the test analogy is quite useful. If you had a test and it was out of 50, that's the total that it's out of. And if you scored 40 out of 50, hopefully you guys could go ahead and work out your percentage. If you scored 40 out of 50, we would then ask, how much energy, or how much did you get wrong, essentially your error. Well, that would be what the total test was out of, minus what you scored, over what the test was out of. And that gives you 0.2 or 20% error. Okay, that's the mistake you made. You made 20% errors in that test, and that would be the same for an efficiency on a machine. This would be a 20% efficient. There'd be 20% of the energy would be lost. So that would be going in some cases to heat or sound. Now, to get the actual efficiency, you would just put in your score. So 40 is what you actually scored. That's essentially the efficiency you had on the test. And that's going to give you 0.8, otherwise 80%. So you would say you were 80% efficient on that test. All right, a little quick example, and then over to you for the rest of the homework questions, and you can call it a day on the energy series. All right, here we have a little electric car. Let's do a little picture. We like to draw pictures. Here's an electric car, and it's got a motor in there that is 80% efficient. And the motor is rated at 140 watts. Now, this car is going to start from 0, and it's going to move for 3 seconds. And after 3 seconds, it reaches a final velocity, and we're going to try and work out what that final velocity is. We also know that the mass of the car is 0.9 kilograms. Okay, so if this engine was 100% efficient, we would say that the change in the energy divided by the time is 140 watts. Okay, so if it was 100% efficient, and this would be, it's 140 watts, in other words, that is a change in the energy per 1 second. Now, this event takes 3 seconds, so we would simply take this value, multiply it by 3, and that would give us the total change in energy. All right, well, what's the total change in energy got to do with anything? Well, in this case, there's an initial EK, which is to do with it being at rest, so that's 0 joules. And then there's a final EK, which would be this 1/2 mVF squared. In other words, there is a change in the energy, and that change in the energy is going to be the difference between the two, so the final minus the initial. And that is equal to this change in energy that we have going on with the watts. Now, one slight difference is that this engine, although it's rated at 140 watts, it's functioning at 80% efficiency. So we need to say that it's actually 140 watts times 0.8. And that's going to give us 112 joules. So we're saying that the change in the energy for this event is going to be 112 joules. Sorry, that's actually joules per second, because that's watts. So it's 112 joules per second times the 3 seconds. Now that's important because look, the little seconds cancel out and you're left with 112. So the change in energy that the motor is doing and is making available for the motion of the car, taking into account the heat and the energy loss, that 20% energy loss, is going to be 112 times 3, which is, what is that? 336. So 336 joules is the change in the energy, and that is equal to the EK final minus the EK initial. So we're going to restate that. We're going to say 336 joules is the delta E, and then the EK final is going to be 1/2 mV final squared minus the EK initial mVI squared, except of course this is 0 because it starts from rest. So to find out the final velocity, we're going to go final velocity is equal to 2 times the 336 joules, divided by the mass, which is 0.9 kilograms, and then square rooted. So the final velocity is 27, and I'm to two significant figures because of that, the two used in the question, 27 meters per second.